Okay, good morning, everyone. Let's get started. Undergrads, you're working on assignment 4, grads 7 and 8. Any questions? Smooth sailing so far? Going once? Okay. All right, so we started last time our history of evolutionary robotics that goes all the way back to 1994. We started talking about the first of 2 papers that was published in that year that introduced this idea of using this evolutionary algorithm, where evolutionary algorithms had actually been around since the 1970s, possibly the 60s, depending on how you counted. So it's basically bringing these 2 ideas together, robotics and evolutionary algorithms. As I mentioned last time, physics engines weren't invented until 2000, so the experiments we're seeing today were all carried out on physical robots. We'll finish up that lecture today, and then we'll move into a sub-theme on minimal cognition. So following those first 2 experiments, researchers headed off in a lot of different directions. One of them came to be known as minimal cognition, which was the idea of trying to boil down the complexity of the robot, its controller, and its environment to something very, very simple, to demonstrate that the robot had evolved some of the building blocks of intelligence. You remember our discussion when we talked about the history of AI. It's very difficult to actually define what intelligence is, let alone define it formally and then turn it into code. So a lot of folks working in robotics have said, forget formal definitions. We're going to just make machines that exhibit behavior that if we saw that in nature, we would consider that intelligent behavior. For a lot of roboticists, that's kind of considered the physical Turing test. If it looks as if it's acting intelligent, then it's intelligent. Yeah? Okay. We'll look at 2 different experiments from this subfield of minimal cognition, and we'll see how the investigators evolved various building blocks of cognition. And then next week, or possibly the week after, we'll get to another branch that roboticists headed off in, which is as the hardware started to improve in the 90s and into the 2000s, it got easier and easier to make more and more complex mechanical devices, including those that had legs. One of the challenges for mobile robotics, as the name itself implies, is mobility, getting from point A to point B. Obviously, it's an easier thing to do if you have wheels rather than legs, but wheels have a bit of a disadvantage. What's the disadvantage of wheels? Why don't we just make all our robots out of wheels and be done with it?
It limits the kinds of terrain they can traverse.
Absolutely, right? So it's limited to certain kinds of terrains or environments. If we want to deploy intelligent machines that live and act and work and play alongside us here in the real world is physically complicated. And one way to deal with that, if you have to get around in that world, is legs. An interesting twist of robotics is that we actually figured out how to make machines fly before we figured out how to get them to walk and run. We're still working on walking and running. In retrospect, flying turned out to be a lot easier. No one saw that one coming. Okay. All right, we'll get to wheeled and legged and locomotion and flight a little bit later. Back to the first years of evolutionary robotics. I mentioned the first experiment was carried out on the Kepler robot. It's a little confusing. I've got 1996 here. That's when the Kepler robot was commercialized. Kepler robot was actually developed in the universities before that time. The Kepler robot was used in 1994 for the experiment we were talking about last time. Sorry for the confusion there. Okay, so we've got this little hockey puck-sized robot called a Kepler. We can stack various things on top. And we saw last time how the investigators wired up 8 proximity sensors to 2 motors with a total of 16 synapses, which means that they needed their evolutionary algorithm to find a good set of 16 numbers that when labeled on the synapses produced a robot that would race through this maze around and around, either forward or back. We ended last time by seeing they did manage to evolve a robot that does this. It's not perfect. It's pretty good. And we ended last time by looking at this plot in the lower left, where we're looking at these 3 different fitness components. There are 3 different things that the investigators wanted their robot to do. The computer calculated the quantity of these three behavioral features for every robot with every controller, multiplied them all together, and you can see the evolutionary algorithm trying to balance these terms out. It's a difficult thing to do because for some of these terms, and we'll see this over and over again in many other experiments, evolutionary improvement to one trait tends to take away from another one. Yeah? Can you think of examples of that from nature? Where does evolutionary improvement to one trait or one behavior for an organism over time caused it to degrade another one?
Whales.
Whales, how so?
They can swim, but they can't walk anymore.
Absolutely, right? If you want to swim really well or you want to move over land really well, you usually have to give up biomechanically your efficiency in movement through other environments. And again, obviously, we'll see that when we talk about the biomechanics of locomotion. Other examples? Yes? Sorry? Penguins, great example. They've made some pretty extreme trade-offs. How so? Sorry? Absolutely, right? So they had to give up flight for water and also for being able to survive in very cold temperatures. Other examples?
Land animals evolved to breathe air, and now they can't breathe in the water.
Absolutely. Okay, lots of examples of the land, air, water transition, right? Another reminder that there are no optimal solutions. However we end up making intelligent machines, they will not be perfect because there is no formal definition. We are not perfect. We are better at certain things, not so good at others. And that's going to have real practical consequences when we think about legislating or actually deploying large numbers of robots in the real world, right? This is kind of a scary proposition to think about deploying perfect machines, right? Our laptops and phones are not perfect either, but they're pretty specialized machines and they're getting more closer to optimal for whatever it is we want them to do, technically at least. Harder to do when you're dealing with the real world, where you have to juggle lots of different kinds of behaviors.
Can you, when you run these experiments, can you run it on one fitness function for a while until you get some basic behavior that you want, and then swap that to a different fitness function to try to extract more complex behavior?
That's a great question. So why not evolve against one of these fitness components or one of these behaviors until it gets pretty good, then either swap it out and swap in something else? Absolutely, and that's exactly what we're going to see in the second of the two experiments reported in 1994. That has become a whole research field in itself. For those that are interested in machine learning, it's known as curriculum learning. What do you teach a robot, or what do you teach a neural network first, or in what order? In all faculty meetings, the biggest argument we have every time is curriculum. What should you all learn first, and then this, and then that? What should be prerequisites? How do you order the digestion of knowledge in order to, in the long run, digest as much as possible? It's an unsolved problem for humans, an unsolved problem for machines as well, but a fascinating one. Great question. Okay. All right, we'll see an example of that in a moment. I'm going to skip over this slide. You can have a look at, for those that are interested in the visual display of information, this was an attempt for them to try and show basically this information again in 3 dimensions. They're trying to plot on the 3 axes here, these 3 fitness components, and then they've tried to visualize evolution as a walk through this 3-dimensional space. You can imagine each point here, each point is one of the controllers that was tested on the robot, and its left-right position, its forward-back position, and its up and down position inside this 3-dimensional space represents how well that controller was at these 3 fitness components. And you can sort of see how evolution is making some progress here. Okay. Okay. Couple of things, other things to point out about this very first evolutionary robotics experiment. Again, it's not perfect. You might think that something that is bilaterally symmetric, meaning that things on the left side of the robot's body are the same as the things on the right side of the robot's body, that might be a path to optimality. It turns out that that's actually worse than what evolved. So let's have a look at the neural network controller down here. Remember that the investigators set some of the contralateral and ipsilateral connections to have inhibitory and excitatory connections to force evolution to come up with some version of the coward. Turn away from proximity, turn to the left if there's lots of proximity on your right, turn to the right if there's lots of proximity on the left. This is an example where they actually hand designed the synaptic weights as well, the magnitudes and not just the signs of these synapses. The width of the synapse represents the magnitude of the value. So you'll notice these synapses that are close to center have larger magnitude than those that are off center. They tried to basically manually design a coward, something that would drive straight as quickly as possible, but also turn when it gets close to something on the opposite side. It's basically the Bradenburg vehicle, the coward. They took this manually designed robot and they placed it at this position in the maze. And they pointed it into this corner here. And you can see from these line segments what the robot did. It started driving forward very quickly. And then as it started to wedge itself into the corner, it would turn a little bit to the right, and then a little bit to the left, a little bit to the right, a little bit to the left, and ground to a halt and stayed there forever. Why?
Because it has just as much input going right as left.
Absolutely. It's bilaterally symmetric. So it's getting, in this case, it's entering an environment in which from its perspective, the world looks the same on the left as it does on the right. And it's got the same sorts of responses for those situations. So it's going to do exactly the same thing. So you might, maybe yes, maybe no, you might think, okay, an optimal solution would be some sort of bilateral symmetry. We're going to make this robot perfect. It turns out that that idea of perfection of symmetry is actually a bad thing to do. It's a little non-intuitive, but again, a reminder that evolution is a satisficer, not an optimizer. And some of her solutions are pretty good in ways that you might not think. So pretty good. Here's an example of the evolved robot. They put it at exactly the same position, facing into the corner. And in this case, the robot turned to the left and got itself out of the corner, made a 180, and headed up along this alley.
Is it a coincidence that it turned in the direction that they had trained it to go around?
Is it a coincidence that it turned in the direction in which it actually evolved to drive around the maze? That's a great question. I'm not sure. I don't know if they reported the actual synaptic weights. You could try and actually probably reconstruct this experiment and try it out for yourself. Yeah. So something that is, whatever this solution is, it's not quite bilaterally symmetric. The distribution of magnitudes of synapses across the left and right side of the body, not the same. And that's apparently, in this experiment, a good thing. Yeah? Okay. Some other interesting things they observed. The evolved controller evolved to drive at 48 millimeters per second, but the motors attached to the wheels could actually spin the wheels at 80 millimeters per second. It never got there. It sped up the robot. The evolution increased the speed of the robot for the first 50 generations or so, and then kept the speed of the evolved controllers at about 48 millimeters per second for the rest of evolution, even though evolution could have squeezed more speed out of the robot, which would have given it a higher V, which would have been a good thing. Why did evolution not do that? Any ideas?
The physical limitations of the robot, like how quickly the wheels can stop moving and the friction of the wheels and response rate of the proximity sensors.
The last one, yeah. So lots of physical constraints here. So the wheels could actually spin at 80 millimeters per second with the weight of the robot. So it wasn't the weight or the friction of the robot slowing it down. It could move at 80 millimeters per second. If you were good enough at remote controlling this, you could, in theory, drive this thing at 80 millimeters per second around the arena. The reason why not is the speed of the refresh of the sensors. So the proximity sensors, remember, are sending out this ultrasonic pulse, and measuring the amount of time it takes for the pulse to return. They're doing this at some fixed frequency, and again, I don't remember what that frequency was, but it was slow enough, sort of the update of the perceptual system of the robot was slow enough that if it went any faster, at one point in time it would be comfortably far from any obstacle, and at the next blink of its eyes, almost literally, it would be in collision with the wall. So this speed, whatever it is, was just fast enough that the robot could sense it would collide with the wall at the next update of its sensors if it kept going, so it turns. Yeah? We don't know what all of these physical limitations are and technical limitations of the sensors and the motors and so on. Again, luckily for us, evolutionary algorithm is figuring out all these dirty details for us. Right? With a different robot, it would be some other top speed that was possible. Right? We don't have to figure out all these details ourselves. That's what the evolutionary algorithm is for. Okay, any other questions about this before we move on to the second of the first evolutionary robotics experiments? Yeah. Okay, meanwhile, while the researchers were finishing this experiment in Switzerland, on the other side of the English Channel, at the University of Sussex in Brighton, UK, a group of researchers led by Inman Harvey here were creating a very, very different kind of physical robot. It's a little bit crazy when you look at it. It's even crazier when you understand the details, but bear with me here. This came to be known as the Gantry robot. They took a regular table, cut out the top of the table, so they just left the frame of the table, and then they made this wheeled trolley car with wheels that could drive back and forth along the x-axis of the table. On top of that big X trolley was sitting a smaller Y trolley that could drive with its wheels up and down the length of the X trolley as the X trolley is driving back and forth along the X dimension of the table. So far, so good? Okay. And then down through the center of the smaller of the two trolleys, they placed another device which is basically an upside-down periscope. So you remember on submarines, you have this camera that comes up and looks around above it. This is an upside-down periscope. There's a camera dangling on the bottom of this boom, and that camera is actually pointed straight down at the ground. A little bit strange. Last little detail here. Just underneath the downward pointing camera, they placed a small circular dental mirror. And this circular dental mirror was attached to a motor that would rotate this angled dental mirror around and around and around. So basically, the robot is looking upside down underneath the table, 360 degrees around itself horizontally. Hopefully I've painted the appropriate mental picture in your head. Make sense? Okay. What you're going to see in a moment is a similar setup now where they have all the electronics, of course, sitting on this desktop device. This detail is the same as the Italian researchers. They have an evolutionary algorithm running on this desktop computer. This evolutionary algorithm is coming up with a population of vectors. Each vector contains all the weights for the synapses that are going to control this crazy contraption. As you'll see in a moment, the control is basically driving the two trolleys, the X and the Y trolley. So there's one motor that controls the wheels of the X trolley, a second motor that controls the wheels of the Y trolley. And I mentioned this third motor down here, which is spinning the dental mirror. That third motor, it just spins at a constant rate continuously. It's not being controlled by the robot. You can think of this as like an autonomic response. It's like your heartbeat, it's always, always going. It's just allowing the robot to see continuously 360 degrees around itself underneath the table. Okay. And then as you can see in this cartoon, they can place little things on the ground underneath the table and evolve the robot to do various things. Why the heck would you create such a crazy contraption? There's a good reason for it.
I'm not really sure how, but the first thing that comes to mind is it might be like very measurable. I don't know, to like see its progress depending on what they want to do.
Measurable? Yeah, you're on the right track.
It distills down all the movement in 2 dimensions into the X and the Y direction.
You have something that's moving around in X and Y. But so did the Italian researchers. They had their Kepera on the table that would also drive around in X, Y. It does kind of, this actually, it doesn't seem like it, but it actually simplifies things in a particular way. It simplifies some aspect of an evolutionary robotics experiment. Any idea what it is?
I could be wrong, but it seems like you don't really have to worry about the robot like falling over or getting stuck or anything like that, because it's on this trolley that has like, I can't see any way it would like tip over.
Exactly. It can't tip over. It can't fall over. All of the wires are out of the way. They're all lifted up through the boom, so there's no real obstruction here. Remember when we talked about this experiment? This experiment took almost 3 days. And each run of the robot took about 10 or 15 seconds. It depends. These researchers, over a span of 3 days, every 10 or 15 seconds, they had to reach in, grab the robot, and put it back to the starting position in the arena for the testing of the next set of synaptic weights. Yeah? Imagine doing this every 10 or 15 seconds for 3 days. At the beginning of the course, you'll remember I showed you the nonaped, this 9-legged robot that was made up of pistons, these 2 Stewart platforms that was in this wooden cage. That robot was actually really strong. We had to close off some plexiglass when it was moving. Same thing in that experiment. Every 20 seconds, someone had to climb into the cage and take the nonaped and put it back to the leftmost side of the cage for the next test. Guess who ended up being the most junior member in the lab at the moment and got stuck with that job? I've got a bad lower back. I think it's from that experiment. So, our very bright British researchers realized this at the outset, and they built this system so that with the press of the button, it would basically reverse all the motor commands that had just been sent to the 2 trolleys from whatever the neural network was, and it would basically back itself back into the initial conditions. Yeah? So much more automated than the other experiments. Okay, so that's why. All right, let's talk a little bit more about the robot's sensors for a moment. So as I mentioned, we have this downward-facing camera, this continuously rotating dental mirror, which gives you back a pixel array, and they drew it here as a square, but you should actually think about it as basically a connected cylinder, the inside surface of a cylinder. Yeah, you've got all these raw pixels of everything you see around yourself horizontally. They converted this down into polar coordinates. Doesn't really matter for our purposes why. So they've now got a top and a bottom and a theta here. Basically, this is the visual field of the robot, which for our purposes you can still think of as the inner surface of a cylinder. Yeah? Okay. Electronics in the early 1990s were not very fast, so it didn't make practical sense to take the RGB, the red, green, blue components of every pixel in this pixel array and send those thousands and thousands and thousands of values into a neural network. Today, in deep learning, that's what we do. You can send thousands or millions of raw pixel values directly into a neural network for pattern recognition. This was not practical, especially for robotics in the early 1990s. So instead, in this experiment, they have a vector which encodes all the synaptic weights for the neural network controller, and then they tacked onto the genome, which is, again, the encoding of the numbers needed to solve the problem. They tacked on 9 additional numbers, 3 sets of 3. Each triplet of numbers specified the x and y position of a receptive field, otherwise known as a fovea. Each of you has one fovea at the back center of your eye. Fovea is basically where you can resolve an image. So 3 sets of 3 numbers. The first 3 numbers dictates the x and y and radius of this circular receptive field, or this circular fovea. We have 3 sets of 3 numbers. So basically, the genome is saying, here's all the weights for the synapses, and I also want you to drop 3 circles into the robot's visual field. I want the robot to focus its attention on these parts of its visual field. In each of these 3 visual fields, at every time step of the experiment, while the physical robot is running, whatever the raw pixel values are inside each of these 3 fovea, they throw away all the color information, they keep just the grayscale values, and then average the grayscale values inside that circle. So at the end of this visual pathway, during one time step of the operation of the robot, it gets raw pixel values back from the camera, but ends up spitting out 3 numbers, which they also downsampled to integers between 0 and 15. It's a bit of a detail, but doesn't really matter for our purposes. They're basically, obviously, restricting the robot's ability to see detail and ending up with 3 numbers, the amount of brightness inside these 3 fovea. As you'll see, for the task that they evolved this robot to perform, that was enough information for what they wanted the robot to do. Yeah? So like we've seen before, where we have 4 touch sensors or some angle sensors, we now have 3 visual sensors, 3 numbers telling the robot basic information about stuff around itself. Yeah? This robot has 4 additional sensors, which are touch sensors. They put underneath the camera this little plastic disc, and as the robot was moving around underneath the table, if this plastic disc under here came into contact with any objects, that disc would get bumped, and this little rod here would bend. And depending on the angle of the bending of this rod, they would set one of the 4 touch sensors to 1 and leave the other 3 touch sensors 0. What are these 4 numbers? These are meant to represent the front left of the robot, the front right of the robot, the back left of the robot, and the back right of the robot. A little non-intuitive because obviously this robot strictly doesn't really have a front and a back or a left and a right. They calculated the virtual front and the virtual back of the robot, and the virtual left and the virtual right, depending on the combined motion of the 2 trolleys. So if the 2 trolleys were moving such that the turret or the camera was moving in this direction, then obviously this is forward, this is left, and so on. If the robot was moving in this direction, this was front, left, right, and so on. Yeah? All right, so the robot is moving around, and at every time step, we're going to input to the neural network controller 7 sensor values, 3 visual, 4 tactile. Make sense? A lot of this was obviously just to deal with the limitations of electronics at the time. Interestingly, this is the first time we've seen an evolutionary algorithm that's evolving something other than just the brain of the robot. As promised, as we move on, you're going to start to see more and more evolutionary robotics experiment where they're expanding the genome to describe or modify more and more parts of the robot's body, brain and body. Yeah? Okay. And this robot has, so we've got 7 sensors and two motors. The values sent to the wheels of the X trolley and the values sent to the wheels of the Y trolley. Yeah? Okay. All right. Someone was asking about curriculum learning before. What order do we teach the robot to do things in? In this experiment, they ultimately are going to paint, or they're going to paint black. They're going to paint black shapes onto the back wall underneath the table. In this particular experiment we're going to talk about, they didn't actually place obstacles on the ground. It was a visual recognition task. So they actually had a black triangle and a black square, and they could place it underneath, on the inner wall underneath the table. And they wanted to evolve the robot that would move away from squares or rectangles and towards triangles. Relatively simple task, yeah? But it's quite challenging, especially when you're moving. Yeah? Okay, so they, again, tried this out from just starting with random sets of synaptic weights. They were not able to evolve a neural controller for the robot to solve this task. So they started with something simpler, and once they evolved the simpler behavior, they paused the evolutionary algorithm, changed just the fitness function, and then continued evolution. Once evolution could solve this intermediate task with intermediate complexity, they paused the evolutionary algorithm again and then swapped in this third most difficult fitness function, and they did manage to evolve a robot that would move away from the square and towards the triangle. Okay. First task is they're going to actually evaluate every neural network controller 4 times inside the robot. So they've got one vector with all the synaptic weights plus the 9 numbers encoding the fovea. They're going to download that onto the robot, drive the turret so that it's at some particular XY position under the table, and then let the neural network controller control the robot. Press enter, it reverses what it just did. Then they send the turret to some other random XY coordinate, and with the same neural network controller, they let it drive the robot again, a 3rd time, a 4th time. They want to see for that particular neural network controller and that combination of fovea, how well does the robot do on average? This is something that might come up in your final project as well. If you're evolving the robot to do a complex task, it might get lucky. Depending on its local environment, it might actually do what you want. But if you change the environment a little bit, or the relationship of the robot to its environment, it's no longer able to do the task. So you might want to evaluate a single robot multiple times and set the fitness function to its average behavior. Yeah? Okay. So in this case, we have a summation over 4 iterations. They're going to compute something, yi here, 4 times for these 4 trials for a single neural network controller. Yi is simply the perpendicular distance from the back wall. So they basically want to see how close the robot gets to this back wall when they start it from different XY positions underneath the table. Not too difficult. Didn't take them a lot of generations to evolve a robot that does that. Yeah. Once they managed to evolve a controller that in all 4 cases would drive directly towards that back wall, they swapped out this fitness function and swapped in this slightly different one, which now they computed the difference between the robot and the center of this black square that was placed on the back side of the table. Doesn't show it in this experiment, but they not only changed the initial position of the turret in these 4 cases, they'd also either placed this black rectangle back right or back left. So again, to demonstrate that the robot isn't just memorizing to go to the back right underneath the table, that the robot would go towards wherever the black rectangle was underneath the table. So far, so good? Is a good solution a low value of phi here or a high value of phi? Low value. In some experiments, they're trying to minimize the fitness function. They're trying to evolve solutions that minimize the fitness function. In other experiments, They're evolving solutions that maximize the fitness function. Obviously, it doesn't really matter in the experiment itself. Typically, we talk about this as the fitness function, and usually that implies more fitness is good, right? Fitter is better. In machine learning, they often talk about loss, which is the amount of bad stuff that happened. You lost something, so they often want to minimize loss. This is something that's confusing in machine learning and AI and robotics. There's no standard. Sometimes people are maximizing things, sometimes people are minimizing things. Sometimes I'll point out which it is. Again, it doesn't really matter for our purposes which is which. Okay. They're still running the same evolutionary algorithm. They've now evolved a robot that consistently will drive towards the back center of the rectangle. Once they get a solution that's good at that, they swap out that fitness function and swap in this third fitness function, phi 3 here, which again is going to take the average or the total over 4 trials of this thing. What is this thing selecting for? In plain English. There's the math. We want to maximize some of these distances and minimize some of these distances in order that it avoids the back rectangle and drives towards the black triangle. Which distances do we want to maximize? Which do we want to minimize?
Minimize distance from the center of the triangle.
Minimize distance from the center of the triangle.
Maximize the distance from the rectangle.
Absolutely, right? So wherever you start, and where you start is the uppercase D's, so there's an initial distance. Whatever that initial distance is from the triangle, make it less. And whatever that uppercase D is between you and the rectangle, make that bigger. Yeah? Okay, I'll leave you to figure out all the negatives and positives there. What do you think the alphas and betas are for? Why include those?
Can you weight it such that we care more about driving towards the triangle or driving away from the rectangle?
Absolutely. So in the previous experiment, we saw they multiplied all the different things they wanted the robot to do together, which was their way of saying you have to do all these things. You're not allowed to ignore any of them. None of these terms can go anywhere near 0, or you get 0 in total. This is a little more forgiving. They're not multiplying, they're adding or subtracting. And when you add or subtract the terms together, then obviously you can weight them as well. Yeah? I don't know if they reported the actual values of alpha and beta in the paper, but again, this is a little trick that might be useful when you come to your final project. There might be certain behaviors that it's kind of okay if they're there, but they should be sort of less. But this behavior, you absolutely have to do. Yeah? You can play around with that by adding these weights into whatever fitness function you end up creating. Questions? Okay. All right. Again, I apologize for the quality of this figure. I'm going to try and zoom in on it, actually, because we're going to talk about this. Actually, first, let's talk about the upper left, and then we'll talk about the neural network controller that causes this behavior. What you're looking at in the upper left is the best evolved controller at the end of this third phase of the evolutionary algorithm. This here was the best neural network controller at getting the turret to avoid the rectangle and go towards the triangle. How to read this? You'll see little start points here. Here's one of the 4 initial random positions. Here's the second initial random position, third one, fourth one. How did the robot do? Is it optimal? Why is it not optimal? How do you know it's not optimal?
It's not just going in a straight line towards it.
It's not going in a straight line. It's actually in 2 of the 4 trajectories describing a spiral. Why? Seems strange. Now remember, this isn't the turret itself actually spinning about its long axis. This is the way in which the 2 trolleys are driving, which causes the XY position of the turret to change in this particular manner in this trajectory. Why would it evolve? Why would evolution evolve the thing to drive in this way?
It might need to gather, like, pictures from different angles of the triangle and rectangle to be able to tell which one is which.
Yeah, exactly, right? This is not just a motion, this is not just solving a locomotion task or a motion task. It's solving a sensor motor task. It's got to be able to see and distinguish things in its environment while it's moving. Remember that this dental mirror is continuously spinning, so at every point in time, it already sees 360 degrees around itself. It's not like it's moving like this because it can't see certain things in its environment and it's moving to reduce or minimize the obstruction or the occlusion. But it does have to do with its ability to distinguish between these two shapes and quote unquote know which one to chase after. Hard to see why this helps, right? Okay, let's have a look. Let's dive into the brain of this robot. And let's see if I'm smart enough to figure out how to zoom in on this. There we go, okay. Okay, so let's start with the visual morphology of the robot. In this case, remember that evolution could create three fovea. Here's evolution showing off. It actually evolved the radius for the third fovea to be basically 0. So it says, I don't need 3 fovea for this task. I only need 2. And I need them in these sizes and at these relative positions to one another. Yeah? Okay. I also don't need the bump information because you didn't put any obstacles in my environment, so I'm basically ignoring my bump information. What does it mean for a neural network to ignore something? Remember that we have our normal input layer here, our input neurons that are receiving values from the sensors, and these are being passed on somehow through synapses to the motor layer. How does an evolutionary algorithm evolve synaptic weights? To ignore, for example, this sensor information. If it's not useful to the robot, there's a way that evolution can kind of set the weights to ignore this information.
Like a weight of 0 or something.
If all of the outgoing synapses evolve values that are closer and closer to 0, that's basically evolution shutting off that sensor. It can do that with hidden neurons and all sorts of things. So just because we give evolution the possibility to flow information between a whole bunch of different pairs of neurons, all of that might not actually be useful, and it might actually be distracting, right? So something humans do all the time. We try and ignore a lot of our incoming sensation and focus our attention on just the our relevant sense modality. Right? For our purposes today, hopefully that's your ears and your eyes. Yeah? Okay. All right. So the robot has a total of 7 sensors, but this controller evolved the ability to ignore 5 of them and only use 2 of them. The amount of brightness in fovea 1 and the amount of brightness in fovea 2. So far, so good? So when they drew this, they just didn't draw all of the neurons and synapses that were connected with 0 weights. Yeah, so there's a lot of the material here that evolution has basically pruned away. You'll notice in this case we've got the input layer on the left here, and we've got the outputs on the right here. Here's the left motor. Here's the right motor. They're just the 2 motors. I don't remember why there's a third one here. Doesn't really matter for our purposes. What are these neurons that are in the center here that are neither sensor neurons nor motor neurons? Test our neural network terminology here. Anybody remember?
Or hidden neurons?
These are the hidden neurons. They're kind of hidden or buffered from the real world. So we have values that are flowing in. The solid lines are excitatory connections. So evolution has set the signs of these synapses to positive. The dashed lines are inhibitory connections. Evolution has set the signs of these 1, 2, 3 synapses to negative values. And the magnitudes are whatever the magnitudes are. This robot clearly is able to distinguish between triangles and rectangles. Where is the triangle recognition module in here? Where is the rectangle recognition module in here? How does it distinguish between triangles and rectangles? It's a little more complicated than a Bradenberg vehicle. We've got more than 2 connections, but not that many. It's tricky to see. There's a few hints in the way this is drawn. Yep, idea there?
Is it maybe those neurons down at the bottom?
These neurons down in the bottom, it's hard to obviously tell exactly what they're doing. Where are they getting their sensory, where are they getting their values from? What is influencing these neurons down here? Remember our lecture on artificial neural networks. We talked about excitatory connections, inhibitory connections, hidden neurons. There were some other little tweaks, little bells and whistles that you can add to neural networks that give them certain capabilities.
Like they're based on previous time steps?
You'll notice that not all the synapses are flowing from the left to the right. There are some that are flowing back again. Neuron 5 and 6 here, the 2 hidden neurons. Neuron 5 is influencing neuron 6, and neuron 6 is influencing neuron 5. We've got some of these recurrent connections, which gives the robot memory, the ability to remember things from previous time steps. So this neural network has evolved the ability to remember something. It's a big hint. But what is it remembering? Thinking about thinking is misleading. I promised you I'm going to repeat this term hundreds of times in this class. You might, maybe, be inclined to think, okay, maybe this is the triangle recognition module, or maybe the rectangle recognition module, and it's remembering where the triangle or the rectangle was at the previous time step and continues to head away from it. Mother Nature, biological evolution, doesn't care about our intuitions, and neither does artificial evolution. There is no triangle recognition module here. There is no rectangle recognition module here. But it is remembering something. In some years, people have been able to figure this out. It's very non-intuitive. Any ideas, given all these hints?
Is it remembering which phobia had more light coming into it?
It's remembering something. It's remembering something about the brightness of the fovea, either one or both of them, from previous time steps. Now we're getting really close.
The fact that it only evolved to have 2 makes me think that one is kind of at the top of the shape and the other is at the bottom of the shape.
Getting closer. One of the fovea sweeps over the top of these shapes, and the lower fovea here, number 2, sweeps along the bottom of the shapes.
If like both of them are excited, they could be looking at both of them, or either one of the triangle or rectangle. But if 2 is like looking at like the black shape, but 1 is not, you're probably looking at the rectangle.
Absolutely. So let's simplify even further and imagine we binarize the brightness of these 2 fovea. It's either black or white, which is pretty close to the truth because they used a back white wall and black shapes. Yeah. So if both of these are black, what is the robot looking at? rectangle, maybe, or maybe the triangle, right? It could be that both of these are sitting inside the triangle. What if only one of them is black? It's ambiguous. It's not enough to think about at the current time step whether neither is black, one is black, or both is black. But it's part of the answer. We need to combine it with that same information from a little bit ago.
If you know how long it's been since the change was made,
That's it.
then yeah, you can tell which is the triangle and the rectangle.
That's it. What is the time? What is the time interval between when one of these went from white to black and then sometime later another one went from white to black? Yeah. So imagine that the robot is turning, we're in this trajectory and the robot is turning counterclockwise, and these two fovea manage to hit up against a triangle that's actually drawn like this. I think in the experiment it's actually like this. Doesn't really matter. You can imagine that these two fovea are going to turn black close in time to one another, right? Or maybe simultaneously. A rectangle instead, these same two diagonally aligned fovea, one is going to go dark first, and then some period of time later, another one is going to go dark. The difference in the time interval between these two fovea darkening, that's how the robot distinguishes between triangles and rectangles. And whatever that information is then gets transformed and sent to the two trolleys to control the motion of the robot. Everybody see that? This is one of my favorite experiments in the whole course. It's like a symphony. There's a whole bunch of things that are coming together here that beautifully demonstrate this concept of embodied cognition. This robot has a very, very simple brain. It doesn't need complex pattern recognition to distinguish between triangles and rectangles. This robot has evolved the ability to put a whole bunch of different things together. Visual information, sensory information, movement, it matters that it's moving, memory, time, the time interval at which the fovea darken matters. It's the relationships between all these things, sensation, movement, action, memory, and time, that are combined in just the right way to make it easy for the robot to solve this task. Yeah? When we think about ourselves, or we think about fruit flies looking for the rotted fruit in the back of the room, we don't think of these kinds of solutions because they're very non-intuitive for us to think about. It's easier to think about the fruit fly doing some calculus and computing the approach vector for the fruit, rather than computing something much simpler as it's moving over time. Yeah? Okay. Question?
How did they choose the neural architecture here?
Good question. I think it was relatively standard. So they had all seven input neurons. They put in a bunch of hidden neurons. They wired up all the input neurons to all the hidden neurons. They did wire up the hidden neurons to each other with these recurrent connections. So the researchers thought maybe memory would be useful for this task. It turned out that it was. And then they wired up all the hidden neurons to the motor neurons, but evolution got rid of most of those connections. Yeah? Didn't need them. All right. If in the weeks to come you get hazy on the concept of embodied cognition, come back to this slide. I think this is probably our best concrete example of how all these things are put together. How evolution puts all these things together to produce relatively complex behavior in a simple way. A non-intuitive way, but a simple way. Okay. All right, we got about 20 minutes left, so we are going to move on now to our sub-theme on minimal cognition. We're going to actually talk about minimal cognition experiments in lectures 9 and 10. In both of those experiments, the researchers used a particular kind of neural network, which kind of goes against the theme here of minimal cognition. This particular neural network is not minimal. It contains some additional details beyond what we've seen so far. So we're going to spend a few slides talking about this particular class of neural networks, which is still used today in a lot of robotics. Okay, so CTRNNs, continuous time recurrent neural networks, will break down each word in this name. In order to do so, my apologies, we're going to have to use some calculus. This is the one and only time you're going to see calculus in this class. All right, back to high school calculus. What is the derivative? Why do we all have to learn calculus in school? It turns out that it's useful for tons of things, including, surprise, surprise, robotics. What is calculus? Well, it started when people started to think about rates of change. So on the horizontal axis here we have x. You can think of this obviously as time. Something is unfolding over time, over x. We want to think about some phenomenon, y, that is changing as x changes. If x is time, we're thinking about how y changes over time. And to do this graphically, we want to draw the slope. But it gets harder and harder to think about rates of change as the amount of time or the amount of x that changes becomes less and less and less. If you have a phenomenon that's changing over time and you want to describe how it changes with a delta t of 0, it seems ill-defined. At the time that calculus was invented, there was no good way to actually describe this. So the derivative was invented, which was a formalism where you could actually write down how things change instantaneously. Yeah? This is useful because it allows us to describe things that change continuously over time. If things change discontinuously over time from one discrete time step to the other, which is typically true in computer science, and with digital systems, you can get away with something simpler, which is the difference equation, right? The value of something at time t changes at the next time step at t plus 1. We can write something down like this, for example. But of course, as we imagine a smaller and smaller difference between this time step and the next time step, it gets harder and harder to understand how to write this down. So we switch to a differential equation, which is written as, in this case, dx over dt. The rate of change in x, the thing that's changing, is equal to the rate of change of dt. In this equation, we're writing 1. The ratio between these two things is 1. They're the same. However much t changes, x changes by the same amount. Yeah? Why do we need differential equations? We're going to use them to describe a neural network in which the values in the neurons in this neural network are not changing discretely from one time step to the next. The values in these neural networks are going to change continuously over time. Yeah? Okay, so here we go. In the box here, we're going to build up a differential equation that describes the rate of change of y sub I, where y sub I is going to represent the value of the ith neuron in the neural network. If we have a CTRNN that has 20 neurons in it, that neural network is going to be described by 20 differential equations. Y0 prime, Y1 prime, Y2 prime, dot, 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 all the way through to Y sub 19 prime. I'm not going to force you to write 20 differential equations. What we're going to do over the next few slides is I'm going to gradually reveal details of the differential equation that describe how that neuron changes over time. So if you're taking notes, leave wherever you see a term being introduced, leave the same horizontal distance, leave the white space because we're going to fill that in as we go. Okay, so let's start with thinking about just the ith neuron in a CTRNN that has multiple neurons inside, and we're going to think about how this neuron changes according to this equation. So in a CTRNN, we start by describing the rate of change over time of the neuron. the ith neuron. We're going to describe how this neuron changes over time. The differential equations, remember, only tell us how it changes over time. It doesn't give us the absolute value of y sub I itself. We have to start, when we think about a differential equation, by giving it an initial value. So you can imagine that y sub I happens to be some hidden neuron inside the neural network, and at the first time step of simulating this neuron, let's say we set the initial condition of y sub I to 0. It's a hidden neuron. It hasn't received any signals from any of its incoming synapses, nothing from the sensorium of the robot yet. At the beginning, when we drop this robot controlled by a CTRNN, either into the real world or into a simulator, the hidden neuron starts with the value of 0. And then over time, we're going to see how it changes. It's going to change based on a lot of different things. For the moment, we're not wiring up this neuron to anything else. It's just sitting there by itself. It's got a value of 0. And we're adding just one term to the right of the differential equation, which is the rate of change of this neuron is equal to the negative of its current value. It seems like an odd term to add. There's a reason for it. All of the terms, all the math that we're going to build up in this lecture are meant to represent biological details of real neurons. Let's think about the mathematical intuition for this differential equation first, and then we'll think about why they put it in there in the first place. What biological detail of neurons is this meant to represent? If this neuron has an initial value of 0, how does it change moving forward in time? It doesn't change, right? We plug y sub I in over here. The rate of change of y sub I is 0. A short time later, we stop. Its value is still 0. We plug that into the right-hand side of the differential equation. Nothing happens. If we set the initial value for this neuron to 0, armed with this equation, it doesn't do anything. Let's say we set the initial value of this neuron to 1. Now what happens as we move forward in time? It decreases, right? It starts to degrade. So at some short time period later, it's decreased. The rate of change is proportional to -1. It's gone down a little bit. What happens in the next time interval?
It goes down, but by less.
It goes down, but by less, because at this point, its value is, let's say, 0.8. We plug that into the right-hand side of our differential equation. The rate of change of the neuron at this time is -0.8. It's decreasing by less. What happens over time? What happens at t equals infinity? It approaches 0, but never reaches it. You probably remember the asymptote, right? We get something that goes like this. Yeah? Neurons, remember, can also have negative values. So let's go back and now set this hypothetical neuron to have an initial value of -1. How does this neuron respond over time? We take -1, we plug it into the right-hand side of our differential equation. -1 is +1. The rate of change of this neuron at this point in time is +1. It's also going to approach 0, right? It's going to jump up, and approach the asymptote from below, right? And you can imagine now what happens at all these other points. Whatever we initially set the neuron to, it relaxes back towards 0. The neuron, quote unquote, likes to be near 0. For anyone who knows anything about neuroscience, one of the first things you learn in neuroscience about neurons is this property.
Is it just that things decay if they don't have a stimulus?
If a neuron isn't stimulated, neurons are lazy. If they're not stimulated, they will relax back to basically doing nothing. Why are neurons lazy? Why is that a good thing to do?
Why is that a good thing for a neuron to do? Why is that a good thing for you? You've got 10 to the 11 of these things in you. Why is this a good thing?
Save energy.
Save energy, yeah? What is it, 20% of all your calories go to this thing up here, yeah? Even despite this, your brain is an energy hog. So if the neuron isn't needed, if it's not being stimulated, it'll relax basically back to doing nothing, yeah? So in CTRNNs, one of the things that the neurons in a CTRNN will do is that at any given time, if their inputs or the stuff that's arriving is not very much, if nothing is going on here, this term will gradually push the value of the neuron towards 0. So far, so good? So again, we're going to repeat this pattern. We're going to go back and forth between the math and the biology. We're putting in mathematical complexity to the neural network to get it to act more and more like biological neurons. Yeah? Just a reminder, we're looking at one differential equation, but we have 20 or maybe 200 of them in the CTRNN. They might all have different values at any given point in time, but all of them have the same form. They all have the same differential equation form. They all have minus y sub I. So regardless of what value they all have, they're all gradually decaying back towards 0. Yeah? Okay. Let's add another detail. You may or may not have seen this notation before. They're writing a term on the left side of the differential equation. This is just so we don't have to work with fractions. You can mentally divide both sides by tau sub I, and you get the same thing. It's just easier, obviously, to write this on the left-hand side. Okay. We're going to now just think about neurons that have different tau sub I values. Y sub I is a variable, but tau sub I is a parameter. This is something that the investigators can set, or the evolutionary algorithm can set. It can assign different positive or negative floating point values to this time constant. Let's set our hypothetical neuron here, y sub I, to have an initial value of 1. And we're going to set the tau sub I value to something very, very small, something very close to 0. How does the value of this neuron change over time? We know from this term that it's going to decay down towards 0 but never reach it. But it's going to do it differently now based on this parameter.
It's going to take a lot longer to get to 0.
Going to take a lot longer to get to 0?
It's going to be very quick.
It's actually going to be very quick, right? The tau sub I is on the left-hand side. So think about dividing both sides of this equation by tau sub I. Y prime equals minus y divided by a number that's very close to 0. Yeah? It's going to approach super fast. In fact, depending on how we integrate or we do this over time, it may actually overshoot 0. Imagine at this point in time, we now have its value being minus 0.8. What is it going to do at the next time interval? Somebody just drew it in the back of the room now, right? It's going to shoot way back up. Could actually do this, but it's going to do something like this. This is known as the Woody Allen neuron. I'm dating myself here, right? This sort of this neurotic New Yorker. Any little thing happens. Any little deviation from 0, and this thing goes crazy. It's happy, it's sad, it's happy, it's sad. It's all over the place. It's very, very, very sensitive. Yeah? Okay. You can probably guess where we're going with this. Let's do exactly the same thing. We'll start at an initial value of 1, and we'll set tau to a very large value. What happens now? Very, very slow rate of approach to 0. This is the Eeyore neuron. Everybody remember Eeyore, the mule from Winnie the Pooh? Like to sit around, I'm fine, don't bother me, don't touch me, I'm doing my own thing. Takes huge effort to get Eeyore to do anything other than what Eeyore is already doing. Yeah? You don't have to remember the cultural references, just the math. So far, so good? Okay, we've got 5 minutes left. Let's keep going. This, hopefully in a moment, will look familiar to you. We're going to add some initial value. We're going to add a new value to this differential equation that we're computing at every time step. It's a summation from 1 to uppercase n, where uppercase n is going to represent the number of total neurons in the CTRN n. If we have a CTRN n made of 20 neurons, n equals 20. If we have 200 neurons, we have an uppercase n equal to 200. We're introducing y sub j over here, and the index j is indexing over all the neurons. We're multiplying y sub j by this new parameter w sub ji. Remember that y is a variable, and tau and now w are parameters. These are not variables. We haven't defined them as variables. They're parameters. They're things that are going to be set by the evolutionary algorithm. And as the legend here says, W stands for synaptic weight. So what is this summation term representing? We've kind of seen this in visual form before when we've drawn neural networks.
The dot product.
It's the dot product, yeah, which is computing the influence of all incoming synapses to the, in this case, the ith neuron. Yeah. So whenever this neuron here, it's wired up by y sub j. So this is 1 j uppercase n. These are all the other neurons. The weight of the synapse here, y sub ji, represents the weight of influence of neuron j on neuron I.
Are all of the neurons connected to every other neuron in the network?
Are all the other neurons in the network connected to all the other ones? The math here says yes. We're summing over all the other neurons, and this summation term appears in all the other differential equations for the other n-1 neurons. So in its CTRN n is a fully connected neuron. We no longer have input and hidden and output neurons. We just have neurons, and every neuron is connected to every other neuron, including itself. Right? This is W sub I. Yeah? A neuron with a self connection. It's a special kind of recurrent connection. If all of these W's for one of the neurons is 0, then the neuron behaves the way we drew it before. What this neuron now does, if some of these W's is non-zero, is hard to draw on the board because there's a lot of things influencing how y sub I changes over time. Part of what it wants to do, or it's part of what it's doing, is trying to decay back towards 0. It's trying to do that faster or slowly, but it's also being pushed away from 0 depending on the values flowing into it from the neurons that are connected to it with the synapse, which is all the other neurons. So far, so good? Okay, I think this is probably a good place to pause. You have a quiz due tonight. Undergrads, assignment 4. Grads, you're working on 7 and 8. Have a good rest of your week, and I will see you next week.